Well, let's do some computing, I suppose. I suppose this should be x here. I'm looking at it going, well, maybe not. Okay, there we go, like that. So we're looking at the stoplight formula, or the binomial distribution formula, or the stoplight problem using the binomial distribution calculation. 5 lights, success probability 0.3, independence is assumed. X is the number of stops, all that kind of stuff is going on. The chance of 2 stops, you have to put 2 stops in 5 spaces. That's the number of ways to do it. Stop, stop has probability 0.3 squared, and then 3 goes is 0.7 cubed. It follows the pattern. NCX, x is 2, p to the 2, 1 minus p to the n minus x. N was, here we are, n is 5. K or x, I don't know what to call it. Maybe I should make it k now. I have to put it everywhere then. Let's try that. K, like that, okay. N is 5, k is 2, n minus k is 3. That's what goes up here. Oh, 1 minus p is 0.7. So we just drop all those things in. I haven't picked this though. So 5C2, the way you get that is you go in here, you go clear this out. 5, math, prob, NCR, 2. And I'm going to type it, I'm going to hit enter so I can see what it is. It's 10. And then I'm going to multiply that by 0.3 squared, and then times 0.7 cubed. So 10 times 0.3 squared times 0.7 cubed. Oh, well, that shows me 10 times 0.3 squared. I forgot to get that exponent to go back down again by going over. Times 0.7 cubed. Go over. Okay, so I think I got that one. 2, 2, 2. Okay, go. 0.3087. And here's the chance of 4 stops. 5, math, prob, NCR, enter, 4. And so that's 5 here. I knew that. Times, and then I got 0.3 to the 4th, and times 0.7 to the 1st. This is 0.7. I'll back it up. Maybe. Try it again. 5 times 0.3 to the 4th. Come over. Times 0.7. I think all right. So 5 times 0.3 to the 4th times 0.7 is 0.02835. I think that's right. We have another example here. Spare tires in 7 cars are examined. Typically only 60% are properly inflated. Find the probability 4 are properly inflated. So we're assuming these cars are randomly chosen. If they're chosen all together in some kind of parking lot and those cars have all been there for a long time, chances are the cars won't be properly inflated. And that's the main reason they're not inflated, is they haven't been checked in a long time. So you have to pick the cars randomly. You can't pick them from one kind of parking lot or another, because that'll change the probability from car to car, or block of cars to block of cars. So 7 random cars, 60% chance of being inflated. Find the probability 4 of the 7 are inflated. So the probability the number inflated is 4. We're going to count inflated tires in cars. There's 7 cars. We want 4 to be inflated. These are the number of patterns of which cars had the inflated tires. The rest of them had non-inflated tires. Chance of inflation, number of inflations, chance of not being inflated, number of non-inflateds. 7 cars altogether. We want 4 of them inflated, 3 of them not. And so now I'm going to try to do that the same way. Math. Oh, get out of here. First I have to type 7. 7 Then I go math, prob, NCR, enter 4. And that's 35. And then I'll multiply that times 0.6 to the 4th. I come over times, what's the other one? 0.4 cubed. Come over. 0.2903. 0.290,304, like that. Okay. So that's halfway fun, I think, being able to answer questions like that that only involve things like independence and counting. That's kind of cool. And then there's formulas here for mu and sigma. They aren't really that hard to verify, but it's a complicated procedure because you've got these NCR quantities in the probability statement, and so when you try to sum x times p of x, you end up having to use some identities with binomial coefficients, which I'm just not going to do. How about that? So we'll just give you the formulas because we might need them in a minute. So here's the formula for the mean. It says the number of successes on average is the number of trials times the probability of success. So that says if you did 100 tries and there's a 20% chance of success, then 20% of 100 would be the average number of successes. That kind of makes sense. So that doesn't go against the grain at all, but here this is a harder calculation. This is a standard deviation. We'd have no reason to think it looks like that. It's just something we're going to have to know, and anytime you need it, I suppose we can make it available on a formula sheet. The sigma for a binomial, so we have to have those 4 conditions. We have to be counting successes. Is the square root of np times 1 minus p. So that's the mean there, but this is 1 minus p next to it. That's just it. So if we had a 20-question test, and the probability of success on each question for you is 0.25, and we could assume independence, and then we count number of successes, your score would have a mean of 20 times 0.25 which is 5. So on average you get 5 out of, because of 1/4 of 20, you get 5 correct. That makes sense. And over here we get 20 times 0.25 times 0.75, and then we take the square root. I would make a guess of like about 2.2 on that, but I could be wrong. So we go 20 times 0.25 times 0.75. There it is. And then take the square root. I'm putting 1/2 as an exponent to do that because I like doing that. 1.9365. 1.93, I'm rounding 65. It's really 649. So right around 2. Wasn't too far off in my guess. So there are some calculations with binomial quantities using the formula when they give you n and p, deciding what n and p are and what x is supposed to be equal to in a word problem, and then here are just the formulas for mean and standard deviation. That kind of tells you on average the kind of number of successes you would see, and then this tells the variability in the way standard deviation does. It would help if the binomial distribution was normally distributed, because then the standard deviation has meaning. And so we'll see in some cases if n is large enough, the shape of the binomial histogram looks to be like a normal distribution. So we have the empirical rule we could use, and then the standard deviation is a measurement that we have some understanding of for normal distributions, and so that's a way of hooking everything together as we move along. But right now we just have the formulas for how you compute the values, and we can't really use them for anything at the moment, but we will in the future.